Hello. Hello everyone. Welcome back for the afternoon sessions of the workshop on celebrating 100 years of quantum mechanics at IMSC. We have two speakers in the afternoon sessions. The first speaker is Professor Arul Lakshmi Narayanan from Department of, he's a faculty member and professor at Department of Physics at IIT Madras. And his research expertise is on quantum chaos, quantum information theory, entanglement, random matrix theory, etc. And assume his title also reflects the same. He's going to talk about chaos and the quantum from Einstein to quantum computing. Over to you.
Thank you very much. Pleasure to be here, and I thank the organizers, Subhashish and others, for this kind invitation and putting me in middle of this August series of speakers. So I'm going to talk about chaos from the beginnings of quantum mechanics, kind of grew together, I would say, and then as these siblings tend to do, they departed for a long time and then found each other again in their old age. So that's the story of the talk. So I'm going to first start with old quantum mechanics and classical chaos, kind of introduction to that, but actually brings up some questions which were, whose impact were felt decades later, and quantum chaos came out into its own around 1970, so I'll give an introduction to that field which is continuing today. Then I'll talk a bit about interactions between entanglement and quantum chaos, or quantum information and chaos, which naturally brings in the element of many particle physics. And then my last part will be about quantum circuits, chaos, and what kind of impact it has on today's quantum computing technologies, just very briefly. So old quantum mechanics is the one from 1900 to 1925. It's an era of classical mechanics dominated along with quantization rules of various kinds, like Planck's quantization rule of E equals h nu, or Bohr's angular momentum quantization, which led to the spectrum, the Balmer series of the hydrogen atom. These were all developed into a kind of first theory by Bohr, Sommerfeld, and Epstein as what is sometimes called Bohr-Sommerfeld quantization. And what they had in mind was that you have some classical system in which you have some separate many degrees of freedom, let's say d degrees of freedom, but they are essentially separable degrees of freedom, and you find these actions, integral p dq, around these closed orbits in phase space, and you set them to be some integer multiples of Planck constant. So it's a quantization of action rather than angular momentum. This is a more general rule, and it actually was inspired by and motivated by the fact that action, somewhat mysterious within our classical mechanics courses, is an adiabatic invariant. N is after all an integer, so if you change your system parameters slightly, the change in the physical quantities which is being quantized should not be of the same order. So that's an adiabatic invariant, and actions are adiabatic invariants. Energy, angular momentum are not really that, and so the correct quantity to quantize, it was realized, was the action. And so this was very successful as far as atomic spectra is concerned, of course the hydrogen atom, but also some other low-level energy levels of multi-electron atoms, or at least of non-hydrogenic, let's say, atoms. But still, it was Einstein who, and that's why the title has Einstein in it. I know that there was a lot about how Einstein's view about classicality or determinism is not quite correct in this fantastic lecture this morning. But here he was actually prescient in this, which is all very classical in some sense. He pointed out in this 1917 meeting of the German Physical Society, and I believe his only paper on the quantization of energy, that there's something that cannot be correct with the Sommerfeld Bohr rule, which by the way we study as in essentially WKB quantization, semi-classics in quantum mechanics. And he pointed out that PdQ, this combination, or dPdQ, that is a area in phase space but with individual degrees of freedom, is not a canonical invariant. You can do things in different coordinates and you will get different answers. Now you don't want that, and therefore he realized that there is a small modification, but important modification, that if you have d degrees of freedom, you have to do something different. You can't just integrate out pi dqi for each degrees of freedom. You have to sum up over pi dqi over the number of degrees of freedom and integrate this quantity over some curve in phase space. This quantity itself is now an invariant, is now an invariant, and therefore this integral has a meaning, and this has a meaning which is independent of your coordinate systems. And the ck here are curves in phase space. If you have 2 degrees of freedom, the kind of motions which Einstein had in mind, and which also Bohr and Sommerfeld had in mind, were essentially periodic motions. And so you could think of some higher version of periodic motions, like some coupled harmonic oscillator or something of that kind. And they have the phase space is now, let's say, 4 dimensions in d is 2. You have 2 degrees of freedom, and the orbit is now, the phase space orbit is going around a torus here like this, and now around what orbit do you compute this integral? So he pointed out that there are 2 distinct topologically different curves here. There is one which is going around this torus this way, and one which is circling this radius, the smaller circle, and the one which is the larger circle. And these 2 are not reducible to each other. Every other closed curve can be reduced to one of these closed curves, and around the closed curve itself, a simple closed curve that can be made to a point, this integral is 0. And so actually there are only these 2 integrals, and this curve itself can be over any curve like this. You can topologically change it. You can distort it in some way. That does not change the value of this integral, and therefore there is an absolute meaning to this. And as many degrees of freedom you have a motion which is taking place in this d-dimensional torus, and you have these d actions which can be quantized. So this, he realized, was the correct generalization of the Bohr-Sommerfeld quantization. But he also realized the following, but maybe before that, let me explain this particular picture, which comes actually from this very nice article by Douglas Stone in Physics Today of 2005. I'll mention the full article just very shortly. Is that this is a particle, real space trajectory of a particle moving in a central force potential. As you know, there is angular momentum conservation as well as total energy conservation. And if you look at any point in space, there can be only 2 directions of the velocity. The velocity vector can point in only 2 directions, or the momentum can have only 2 different values at any position. And you should think of this torus, the red, as corresponding to the velocity vectors pointing this way and the other pointing this way. So it's a double, it's a lift, a double lift, if you wish, of this into phase space. So you can see already the torus which is coming out of here because of the double valued nature of the momentum in this. But here is where Einstein asked a question, and this was a critical question. He asked, if there exists fewer than d constants of motion, as is the case, for example, according to Poincaré in the 3-body problem, then these momenta pi are not expressible as a function of these coordinates. And the quantum conditions of Sommerfeld-Epstein, who I believe was a student of Sommerfeld, fails also in the slightly generalized form that has been given here. So first of all, this assumes that you have orbits moving on these tori, and that itself is an assumption which is generally not valid. And Einstein points to the works of Poincaré, who has pointed out that the gravitational three-body problem is of that kind. And therefore, there's a fundamental problem with this quantization. So this was saying that, well, this is good, you have all these quantization rules, but they don't apply to most of the classical systems that you want to apply it to. For example, if you take the helium atom and try to apply it without any perturbation theory, you would have an issue. It is essentially a three-body problem. So what work that he was referring to of Poincaré is a very fascinating work that really has all the beginnings of chaos in it. First of all, what is the n-body problem? It's the gravitational n-body problem. You have n objects which are mutually attracting according to Newton's laws. And you have this bunch of differential equations for those Newton's laws. And the problem was to solve this. After all, something like a solar system evolution, celestial mechanics would largely be dependent on solutions of such equations. And n equals 2, the famous two-body problem, was solved geometrically by Newton and analytically by Bernoulli in 1710. We now study it in our basic courses on classical mechanics. However, when you go to the 3, n equals 3, there are 3 objects that are mutually attracting each other in the gravitational field. I believe Newton said it exceeds, if I'm not mistaken, the force of any human mind. And fast forward to 1885, a bunch of mathematicians, including Weierstrass and Mittag-Leffler, decided to float a prize for the 60th birthday of King Oscar of Sweden and Norway. And Weierstrass stated this problem as, for a system of arbitrarily many mass points that attract each other according to Newton's laws, assuming that no 2 points ever collide, find a series expansion of the coordinates of each point in known functions of time, converging uniformly for any period of time. So you give up the hope of solving it in terms of known functions and just ask that the solution be expressed as some convergent series. And 12 entries came for this particular question. There were other questions also. And Poincaré was awarded the first prize. And actually, there is a whole history of this which I can't go into. It's a very fascinating history. You can look it up. It was revised. Poincaré's first entry, about 300 pages, was revised on criticism and inputs from Fragman. And so his initial attempt at solving this, he revised it completely considerably, and got the prize, although he did not solve this problem. He got it because he actually essentially invented entire dynamical systems in one go, the geometrical theory of dynamical systems. And so many of these notions which we use today, such as the surface of section, taking a high dimensional flow, cutting it and looking at what's happening in that section, originated from this work. The famous Poincaré recurrence theorem, that in any Hamiltonian system, you start from any point in phase space, you're going to come back to that arbitrarily often. Almost all points are like that, was also part of this. The integral invariance, not just the volume, but if you have d constants of motion, there are d integral invariance. That was also there in this. And most importantly, this is where this input from Fragman was there. The transverse intersections of homoclinic orbits, which are essentially the seeds of what was later called chaos only in the 1970s, but was already there, and Poincaré realized the complexity of these orbits. To just give you a very simple idea of this, because that looks kind of a jargonish, it is, if you take a simple pendulum, there exists an unstable orbit which is sitting at the pendulum is sitting at the unstable equilibrium point, and there are 2 orbits which will approach this equilibrium point, one from the left and other from the right, clockwise or anti-clockwise, and they will take infinite time. So these are asymptotic solutions to this fixed point which is unstable. And what Poincaré realized, well, initially he thought that when you generalize these unstable periodic orbits and orbits which are asymptotic to it in positive and negative times, he thought that they will only smoothly meet, like if you're seeing the phase space of the pendulum, these things actually smoothly meet, and he assumed that they smoothly meet, and he actually realized on further reflection and inputs from Fragment that this is not correct. They can intersect not tangentially but transversely, and what is most interesting, if that intersect once, they can intersect infinite number of times. They should intersect infinite number of times. That led to what is called homoclinic chaos. And unstable periodic orbits, the importance of unstable periodic orbits in these kind of systems. So I'll come back to that. So essentially Poincaré in his work laid foundations for modern theory of dynamical systems. But he also proved that for the three-body problem which Einstein was quoting, there are no further integrals of motion than, that is constants of motion, than the ones obvious from symmetries like total angular momentum, total momentum, and energy. And it's a less known fact that actually this problem was solved definitively by Sundman in 1912. He gave a convergent series as Weierstrass demanded for the three-body problem. It was a convergent series in t to the power of 1/3. So it is a remarkable work. Sundman did what Poincaré could not do. But this was for n equals 3, and I believe the graduate student in 1991, Qi Dong, solved this problem for n greater than 3. So it's not correct to say that the three-body problem has no convergent solutions. In fact, the n-body problem has convergent solutions of this kind. But they are actually practically useless. I have not seen a number quite as large as this in a scientific context, but I believe 10 to the power of 8 million terms are needed in this series to do any reasonable astronomical calculation. This was estimated in 1930. And Sundman declares thereafter that numerical integration is really the only tractable method. So yes, the problem can be solved in some sense if you think that this is a solution, but it's completely useless. And this is acknowledged by both Sundman and Qi Dong later on. Now what is chaos? So this is chaos for everyone. Chaos is, first of all, not the inability to solve the equations of motion. As we just saw, even the three-body problem, you may not be able to write it down in terms of elliptic functions or something, but you can have a series. It's not the inability. In fact, there are toy problems of classical chaos, such as these iterations rather than differential equations. Discrete equations such as these, xn plus 1 is twice xn modulo 1 brings it within the interval 0, 1. Twice xn stretches it. So the chaos is basically an action of stretching in phase space and folding it back, and this has both of these actions in it in one go. It can be solved in the sense that if you're given an initial condition x0, you can find out what is xn using this formula, explicit formula. But it doesn't tell you very much about the dynamics at all. The logistic map, another very well-known textbook example, 4xn into 1 minus xn is another example of a completely solvable thing. If your initial point is x0, then you do this and you find the point xn. So it's exactly solved. You wouldn't look at this and say actually the solutions are as erratic as this. This is time xn, and there are two trajectories which I have plotted for some values of x0 that differ by 10 power minus 6. So one part in a million, very close to each other. The blue and red start, and as you can see, it doesn't look like it's from some, it can look like from a random series, but it's not. It's actually solutions to this. And this graph shows two things. One, yes, you can have solutions to something which looks complex. And also another important practical aspect is that if you start 2 points which are very nearby here at 10 power minus 6, they depart very quickly. Here in 20 time steps, they have no correlation with each other, and that is related to the Lyapunov exponent, which says how fast these trajectories are separating from each other. Here the Lyapunov exponent is log 2. So since 2 to the power of 20 is of the order of a million, so that is the time at which they start departing. So chaos has these characteristics. There is sensitive dependence on initial conditions. which for engineers and scientists are more really the definition. But also it's essential that you're talking about bound trajectories, not trajectories which are going away, scattering away. So ergodicity, that is almost all trajectories visit all neighborhoods, is essential part of chaos. And you also have a dense set of unstable periodic orbits. It's not as if every orbit is aperiodic. Almost all orbits are aperiodic, but arbitrarily close to any point in phase space, you will have a periodic orbit. It can be very long and it will be unstable because it's chaotic. So that's actually the hallmarks of chaos: a sensitive dependence on initial conditions, ergodicity in phase space, and the existence of a dense set of periodic orbits. Now, this is from this paper which I mentioned about. So this is the first one where I was talking about the torus. Douglas Stone's article called Einstein's Unknown Insight on the Problem of Quantizing Chaos. So this is what I said about an integrable system, a circle billiard here is shown. That's a central force problem, angular momentum is conserved. It's just a free particle moving inside an enclosure of a circle. It's just reflecting specularly off this. At any point, you have only two possible directions of the momenta, this green and the red. Whereas if you take an enclosure like the stadium with just two straight segments and semicircles here, at every point you can have an infinity of possible momentum directions. So this torus simply disintegrates. There is no torus. At any given point, this momenta can take an infinity of values, so this is a non-integrable system. There's only one constant of motion, namely the total energy. And it's in fact quantization of these kind of systems that Einstein was worried about. He said, well, for circle you can do the generalization which he proposed, but for the stadium there was no way of applying those rules of quantization. Of course, this problem went completely into the back burner from 1926. Well, I don't know how much of appreciation of chaos was there, but nevertheless, with the advent of the quantum mechanics of Heisenberg and Schrödinger, there was no need for these integrals or classical phase space. Everything became Hilbert space, and people were solving eigenvalue problems. Whatever may be the nature, integrable, non-integrable, we don't care. So just to give you an idea of this sensitive dependence, so this problem recurred, as I will say a bit later, in the problem of quantum chaos. But let me show you what happens under this billiard, which is circular, and this integrable billiard. I'm starting from a bunch of trajectories, maybe 5, very close, and then you can see that they do separate. It's not as if they don't separate in time, but they'll separate polynomially in time rather than exponentially, and they would have still very strong correlations. You can see that all the directions are essentially in one direction, whereas if you start the same 5 trajectories from a stadium billiard, you would see this kind of motion here, and you can see how after a very short time, which is essentially related to the Lyapunov exponent of the system, it's moving as if they are in completely random orientations, and this is ergodic, and even a single trajectory would cover this. This is mathematically proven to be completely chaotic system. So generically, generic systems with more than 1 degree of freedom, Hamiltonian systems, will have less than d constants of motion, where d is the number of degrees of freedom, and in principle they can display these features of chaos. Another simple model, which is now 2-dimensional, a map. It's a discrete. I showed you the logistic map, which is 1-dimensional. This is closer to this Poincaré surface of section, which Poincaré was talking. So we always like some very simple models. So here is an Arnold cat map, which is a 2-dimensional area preserving map of the torus. So it's modulo 1 onto itself. And if the eigenvalues of this don't lie on the unit circle, that is, they are real, then actually this stretches things in phase space. Phase space here is this torus, unit torus, and it folds it back because of the modulo 1 condition, and in fact it's known to be, in a statistical sense, isomorphic to a Markov process. So a 3-level Markov process. So let me, again, these are popular simulations. We start with an image on a 256 by 256 grid. So there is Q here and P here, and this is the initial image, and you iterate it once. So Rajnikant is being pulled in this direction and compressed in this direction. Hamiltonian systems have equal pull and push so that the area is conserved. And then this is after 2 iterations, 3 iterations. After 5 iterations, you don't see any of the original image, but all of the information is there. It's not lost, it's just scrambled. The information is scrambled here into this. And this is a kind of process of thermalization, if you wish. Also, where some kind of an equilibrium is reached in a very short time because of mixing. There is now every point, it's not just ergodic, but every region is getting mixed into every other region. You can just think of dropping a drop of ink into water, and you have an equal amount of ink, equal fraction of ink across this region. By the way, it's called a cat map because Arnold put a picture of a cat on this, but we need a superhero there because actually the Arnold cat map has some very interesting Poincaré recurrences and comes back after a long enough time. But that's because of some peculiarities of the cat map itself. So let's not wait for that long, but actually it's about 196, it comes back to itself himself. Yeah, there he is, okay. So classical systems of this kind are well established in some kind of what's called the ergodic hierarchy. Ergodic systems are at the base of this. So here you may think about phase space being equal to time average, or every point visiting a neighborhood of every other point. Mixing is where something like this happens in time, ink drop in water. Kolmogorov is where this mixing or this correlation happens exponentially fast in time. And Bernoulli is kind of at the apex of this hierarchy, where the dynamical system is in a stochastic sense as random as a coin toss. There is one-to-one correspondence between a coin toss and orbits of that system. In fact, it may seem it's difficult to prove these, but some of these billiards have been proven to be even Bernoulli, so it's a very high level of ergodicity in these systems. Okay, so now we come to quantum chaos, which kind of begins in 1979. As you know, there was this because of the availability of a personal computer and computing facilities, one could see what Poincaré could only imagine, and there was a burst of activity as well as development in the study of dynamical systems and classical chaos. So along with that came questions about how will the quantum mechanics of something like a stadium billiard differ from that of a circle billiard, for example. So what are the issues? First of all, there's no phase space. So all the things that we've been talking about, position and momentum, since they don't commute, there is no phase space to begin with. But because of this commutation relation, this h bar has some kind of a coarse graining at the h bar scale. So you could think about taking some classical system and there is some coarse graining at the level of h bar. So there is that issue. And some of these questions were asked and continues to be asked. How does classical chaos impact quantum spectra? One likes to study eigenvalues, eigenfunctions, and so on, or about time evolution, for example. So there are a lot of red herrings in the study of quantum chaos. So let me point out a few of them. There is no quantum chaos because, one, quantum evolution is unitary. So if you take a state here, it's just changing by this unitary evolution, and therefore if you take an inner product of two states, psi 1 and psi 2 at time 0, that's their inner product, or the kind of distance between them, that remains the same at a later time because u adjoint is identity. And therefore forget about exponential dependence. There's no dependence at all between the distances of two states. They don't diverge. Therefore, there's no sensitive dependence on initial condition. So my response to all of this is, but classical evolution is also unitary. Phase space densities in phase space also undergo a unitary evolution. Is e to the power of something which looks like a Hermitian operator. It is a Hermitian operator, and it's actually just the Poisson bracket relation. This is the Liouvillean. So the classical evolution is also unitary in some space, and in fact all of these phase space density evolutions, you could think about evolution on phase space itself as evolution of densities. A point is a density which is a delta function. Therefore, classical evolution is also unitary. Quantum mechanics is linear. Schrodinger's equations are linear equations in time and in the wave function also, and therefore whatever may be your potential, this is a linear differential equation, whereas Hamilton's equations are nonlinear, and nonlinearity is essential for chaos. Of course, Heisenberg equations are nonlinear. I mean, they are the most closest to Hamilton's equations. However, those involve operators and seem like a fairly complex object. On the other hand, I can also argue that quantum mechanics can also be cast as a linear theory with complete honesty, because again, Liouville. So phase space evolution, this is Liouville equation. The total derivative of a phase space density is 0, or this is a partial derivative is the Poisson bracket with this Hamiltonian. That's a linear partial differential equation, and therefore Hamilton's equations are also linear. In fact, at the beginning of quantum mechanics, Koopman decided to have a Hilbert space formulation of classical mechanics, and that's the Koopman operator. He proved that anything connecting for a Hamiltonian evolution is unitary in the space of square integrable functions on phase space. So in fact, there exists a Hilbert space formulation of classical mechanics as well, although I tell students who are trying to solve a pulley problem not to take this route. But nevertheless, from a basic perspective, this is certainly true. So all those things which are said to be a block against chaos in quantum mechanics is also true in the classical domain, and which we know classical domain is very rich with all of these well-established phenomena. So in fact, right at from the beginning, there has been a lot of work towards applications, and here are some of the applications. So I put in heavy nuclei first, although it's kind of motivated from, as I will say, statistical data analysis. But in fact, some of the early models of these billiards were themselves as if they are some, they are particles trapped in a nuclear potential, and that was the early motivations for even studying these kind of things. So strong interaction physics. Some of the early experiments were done with hydrogen atom, the basic hydrogen atom, but now in strong electromagnetic fields. It can be electric fields which were in the microwave region, but with highly excited Rydberg atom states in which ionization was possible. So this was one of the systems in which there was people found it useful to look at it from a chaos perspective, a quantum chaos perspective. The other was going beyond the Zeeman effect, strong magnetic fields of the order of 5 Tesla or so. It breaks the symmetry of the hydrogen atom strong enough for it to develop chaos, from a classical perspective, for it to develop chaos, because if you have a strong magnetic field, you have now a cylindrical symmetry which is conflicting with the rotational symmetry, and it reduces effectively to a 2 degree of freedom problem, which can display chaos. Helium atom, that's a three-body problem. Molecules, water and so on. So there's a burst of activity among chemists, also studying how energy is being distributed in a molecule. You could excite one particular molecular bond and see how it is being distributed. All of that was found useful to study these kind of non-integrable problems. Then mesoscopic transport in quantum dots in the 90s, experiments came up which were looking at conductance fluctuations in very clean quantum billiards. These kind of dots which were looking like the stadium billiard, you attach some leads to it and you pass a current through this. But if the system is so clean that if there are no reflections or there is no scattering of impurities, then it is essentially only the walls of this quantum dot that matter, and people found that these conductance fluctuations as a function of a magnetic field or something was looking random, but they were reproducible experimentally, and they had to do with the chaos inside these billiards, and there were specific signatures about whether there is time reversal or not in these systems. And there's a lot of work about spin systems, the breaking of integrability, phase transitions, and I'll come back to some of these things to do with quantum computers, but now there is a fair bit of work on quantum metrology, which is the science of sensing various things. It could be a magnetic field, could be temperature, or various broadband sensing of this, which is now quantum sensing is one of the important branches of quantum activity. It turns out that quantum chaos is also, or quantization of chaotic systems is something which is very useful in this in quantum metrology. It aids in increasing the sensitivity of sensing. And of course, foundations of quantum statistical mechanics, quantum field theories, quantum gravity, etc. It's quite a, and quite amazingly, there's connections found between the Riemann zeta function, the zeros of the Riemann zeta functions, and quantum chaos. So there's a lot of, I'll come back to some of those things later, but let me go into some very specific models so as to give you some idea of, also to look at some pictures of how things are evolving. So these are models which people have studied both theoretically and experimentally, and they have been useful models. These kind of kick systems where you have a Hamiltonian and another Hamiltonian or another you can think about it as a potential which is turned on and off using this train of delta kicks. These things are useful because you can integrate them between these kicks. So there's a periodic kick, so just after two kicks, if you find out what the position and momentum are, you can write these maps down explicitly. These are the kind of maps that Poincaré was doing for the restricted three-body problem, but now you can write them down analytically, very simple maps here, which would depend on just this potential energy here. For example, if you take this potential energy to be the cosine, so it looks like a kicked pendulum, then this is called a standard map or a kicked rotor. So that is the this is now an area preserving map. So you should just think about this as position, and this is angular momentum or momentum, but it's now discrete, it's not flowing in time. And this is for the, there's a parameter here which is the kicking strength. If there's no kicking, it's just a free particle on a circle. So the momentum is conserved, and this is integrable system. And if this k is not 0, larger than 0, it shows a transition to complete chaos. You can see that for small values of k, by the way, each color is an individual orbit. So you have a wide variety, bewildering variety of orbits and dynamics here. Dynamics which is looking periodic, dynamics which is looking completely non-periodic, aperiodic, and much more complex kind of resonances. These are nonlinear resonances which are happening here. And as this parameter is kicked up even further, all these stable islands here, regular parts of phase space, they disappear in bifurcations, and almost the entire phase space becomes chaotic. So a single orbit just goes ergodically here. It's also a mixing system. And after k is 4, even this island, even this fixed point here loses stability, and for k is 9, for example, you see full chaos here. There's a single orbit, which is this blue color, which is going around. And you can quantize these things very easily because they are just written like this. So between the kicks is just a free particle, and during the kick it is got this cosine potential. So instead of an exponential of a sum, it's a product of the exponentials. So that's the difference between chaos and regularity. So you can quantize such systems very easily, and there's a single parameter here as well as this Planck constant h bar. So we are interested in studying how these systems behave for different values of Planck constant and different values of this kicking strength k. Now here I'm showing you some evolutions of a classical phase space on the left. This is at k equal to 0, and so there's momentum which is being conserved, and the classical bunch of trajectories, I'm starting from many trajectories, they're just diffusing along the angle. Momentum is remaining constant, and quantum mechanics, I'm starting from a coherent state at the origin, and then it's again diffusing classically. You can see till some time there is quantum classical correspondence, and then there is interference effects, there is revivals, there is fractional revivals, and all of that interesting phenomenon occur here. You can see that it's recurring back, or there are these fractional revivals which were studied a lot by quantum optics people, especially in the 1980s or so. If it's non-integrable, like k is 2, and if we start from something which is like an island, you can see classically it gets stuck in some island, but there are these orbits which are escaping that. And quantum also, you can see essentially that it is getting stuck on something like which is a period 2 orbit, but there are tunneling effects and there are these kind of spreads outside. If k is 9, there's complete chaos. You can see that classically it just very quickly it equilibrates, so to speak, it goes away, and in quantum it goes into a superposition of rather complex states here, which are essentially what one may call random states. So that's the kind of phenomenology which this simple model gives, and already people realized that there are some very important time scales in this, and they call it the Ehrenfest time scale, which is telling you how much time you can expect classical and quantum to coincide or be approximately the same. And the scaling of that with a Planck constant or a scaled Planck constant is 1 over square root of h bar for integrable systems, whereas for chaotic systems it is log of 1 over h. Now the log of 1 over h is much smaller than 1 over square root of h bar, and therefore the time scales at which quantum interference occurs in classically chaotic quantized systems is much, much shorter. So you can expect quantum effects to arise at much shorter time scales if there is chaos. So let me kind of briefly mention there is a whole lot of activity. It's been itself now nearly 50 years of this. So there's been a lot of work. So maybe I should start with actually the second point, because I kind of started with a semi-classical theory. As we know, the WKB formula was this integral of P dq is, I'll actually show, maybe I should even show, yes. So Einstein's rule of integrating sum of P dq is just this P dot dq here, was further generalized in the 1950s by Keller, and he introduced these phases, a bit like what Subhash was talking about in the morning, but they are geometric phases, and they are coming from, actually in this case they are arising from classical turning points or caustics, and they are called Maslov indices in general. So for instance, we recognize that for a harmonic oscillator you have n plus 1/2. The 1/2, although we say it's a quantum, it's actually coming because there are 2 classical turning points, and this mu is 2, and therefore you have 1/2 there. So this has been generalized for integrable systems and it's called the EBK, or the torus quantization conditions. for integrable systems. It works for regular separable systems. So what happens for non-separable or three-body-like problems was actually worked out to a large extent by Gutzwiller, Michael Berry, and others using the path integral formalism. And the semi-classical theory, which involves periodic orbits, which, as I said, they are there in chaos, but they are exponentially large in number. They are a dense set of orbits. So a semi-classical theory was developed for this, and for instance here, so you have a density of states of these systems, which were given as a sum over periodic orbits, and these are the stability of the periodic orbits. This is the action of the periodic orbits. So in a sense, this answered the questions of Einstein. If there were no tori, how do we find the spectra of quantum systems? However, this is only the leading order in H-bar. This has been intensively studied. It's a semi-classical bridge between unstable periodic orbits and quantum spectra. It has been used to derive things like spectral form factors for statistical theories. I'll just talk about that, about random matrix theory. And it has been also used in spectra of atoms. It's the beginnings of quantum mechanics, such as the hydrogen atom in a strong magnetic field by Windgen as early as 1988. So it has been and continues to be a very interesting, successful theory, which people are also applying to many body theories at the moment. But it involves finding periodic orbits, which is not an easy task, finding their stabilities, especially finding the periodic orbits and enumerating their actions. So so that was in the 70s, and then there was there's something called the Bohigas-Gironi-Schmidt conjecture, which was formulated around 83, 84 by these three people, who essentially said that if you have a classical system which is chaotic, think about the stadium billiard or the kick pendulum at k is 9, then they said that there is universality in its quantum spectra via their statistical properties. You look at, for example, nearest neighbor spacing statistics, they would be something like a random matrix. So there is a statistical universality which was found. Random matrix theory was developed in the 1950s for these